As we trace the early moments after the Big Bang, we arrive at a state of unimaginable density and temperature. A chaotic, seething soup of raw energy. There were no stars, no galaxies, not even atoms. Just a glowing fog of particles and forces interacting violently in an arena where the familiar laws of physics began to take shape. In this cosmic furnace, quarks and gluons, the fundamental building blocks of matter, jostled and collided. The four fundamental forces we know today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, began to separate from one another. The universe was expanding at a phenomenal rate, and with every microsecond, it cooled just enough for new physical processes to occur. It was a chain reaction, one phase transition after another, each more structured than the last. But the most astonishing part is that this emergence of order came from sheer chaos. Quantum fluctuations, tiny, random disturbances in the energy field, left their fingerprints on the very fabric of space-time. These quantum ripples, born in the smallest scales imaginable, would later give rise to the vast cosmic structures we see today. Clusters of galaxies, voids of darkness, and filament-like webs of matter stretching across the cosmos. It's a profound truth. The seeds of galaxies were sown by quantum randomness. As the universe continued to expand and cool, subatomic particles began to bond, forming the first protons and neutrons. Within the first 3 minutes of cosmic time, these protons and neutrons fused to form the nuclei of the lightest elements, hydrogen, helium, and traces of lithium. This process, known as Big Bang nucleosynthesis, set the stage for everything that followed. And it all happened in mere minutes. But the universe remained dark. The temperatures were still too high for electrons to combine with these atomic nuclei to form complete atoms. The result was a hot, dense plasma of charged particles that scattered light in every direction. The universe, in its infancy, was opaque, a brilliant, blinding fog that no photon could escape. This phase lasted for nearly 380,000 years, until the universe cooled just enough for electrons to settle into orbit around nuclei. This event, called recombination, allowed light to travel freely for the first time. Those first photons still exist today as the cosmic microwave background, a faint, ghostly afterglow that permeates all of space and provides us with our earliest snapshot of the cosmos. Captured by satellites like COBE, WMAP, and more recently Planck, this ancient light reveals a near-perfectly uniform universe with tiny imperfections. And it is within those subtle imperfections that we find the blueprint of everything. Gravity began to work its magic, drawing matter into denser regions and leaving emptier regions to become the great cosmic voids. Over millions of years, those denser regions collapsed under their own weight. Clouds of hydrogen and helium gas began to form, pulled together by the irresistible force of gravity. The first stars were born, titanic, short-lived giants that burned with incredible intensity and forged the heavier elements in their cores. When they died, they exploded in cataclysmic supernovae, seeding the universe with carbon, oxygen, and iron, the elements necessary for planets, life, and everything we know. These stars gathered into the earliest galaxies, vast collections of stars, dust, and dark matter swirling together in dynamic harmony. The universe was no longer a dark fog. It had become a place of light, structure, and unfathomable scale. Yet we must not forget the mysterious players that shaped this entire evolution: dark matter and dark energy. While ordinary matter, the kind that makes up stars, planets, and people, accounts for less than 5% of the universe, the vast majority remains invisible and unexplained. Dark matter, though never directly observed, exerts gravitational influence on galaxies and clusters. It acts like an invisible skeleton, helping galaxies hold their shape and orbit faster than visible mass would allow. Without dark matter, our universe would look radically different, perhaps not even capable of forming galaxies at all. Then there's dark energy, a far more elusive entity. Discovered in the late 1990s, it's responsible for the accelerated expansion of the universe. Unlike gravity, which pulls things together, dark energy pushes them apart, causing galaxies to race away from each other faster and faster over time. Together, dark matter and dark energy dominate the cosmic narrative. They shape the past, present, and likely the future of the universe. And yet, their true nature remains one of the greatest scientific enigmas of our time. We are, in every sense, the byproduct of cosmic processes, shaped by forces we barely understand, and nurtured by the long dance of energy and matter. From the flicker of quantum fluctuations to the birth of galaxies, the universe has been on a journey of astonishing transformation. And through all of this, we've only recently arrived to witness it.